We're alive, March 18th. All right, let's take a look what we have today. We have some notifications. Take a look. Blah, blah, blah. No idea what this is. Doesn't matter. All right, let's do this. Let's see what we have today. 1, 2, 3, go. Wiggle subsequence. Wiggle, wiggle, wiggle. Okay. Doesn't seem to be easy. Can you solve in O(n) time? All right, so it's not going to be easy. 1000, so we can solve in O(n) squared, but we're required to solve O(n). Let's see. Given an integer array, okay, return the length of the longest wiggle sequence. A wiggle sequence is a sequence where the difference between successive numbers strictly alternate between positive and negative. Okay. The first difference may be either positive or negative. A sequence fewer than 2 is a trivially wiggle sequence. So less than 2 is always good. So for example, this is a wiggle because the difference is 6 minus 5 minus, okay? In contrast, this one is not because these two are both positive. And this is a positive, negative, positive, and 0. The first because the first two, yes. And the second because the last difference is, so it cannot be 0, either positive or negative. A subsequence is obtained by deleting some elements from the original, leaving the remainder. So we can, the length of the longest wiggle, so it's a subsequence, right? Oh, so we just remove some elements and the remaining has to be, okay. So the entirety is, and this one, several subsequences that achieve this length. One is 1, 17, 10, 13, probably 10, 16, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the only one, the longest is, how is it 2? Oh, any 3, any doesn't work. So 2 is a 2 or 1. Can we do 1? Fewer than 2. And 2 is always good, right? 2 is always good. All right, we have a little bit question. So let's just take a look. I think any 2 will work, right? Any 2 will work because we only have one difference. Yeah, any 2 will work. And any 1 shall work as well because it says that's a trivial one, okay? So any 2, any 1 will work. And if you have a sequence, so minimum, any sequence, right? Any array, the minimum is 2. You can always have 2. If it's 1, it's 1. If it's more than 1, its minimum is 2. And if it's sorted, either ascending or descending, that's going to be 2. All right, now let's think about it. How do we approach this problem? So we want to find the longest, right? The longest. And it's a subsequence, which means we can pick any one in it as long as the order is the same. So this one, we can just try. We'll go up, go down, go up, go down, go up, and that's good. This one, we have go up, go down, go up, and then we'll go up again. So, which means there might be a optimal substructure there. So we might be able to use dynamic programming. So let's just write that sequence down. 13, 15, 10, 5, 16, and 8. All right. So if we have a 1, then we return 1. If we have 2, then we return 2. If we have 3, when we look at the third one, we'll look at the first 2, right? So the first 2 give us 2. So for the 5, I'm going to look at here. So it either belongs to the previous one, right? It belongs to the previous one, or it So if it belongs to the previous one, then we add it. How do we tell if it belongs to the previous one? So we need to record the previous the sign. So it's a negative. So we just say previous. So at 17, position 17, we have a positive and 2. So positive and 2. So at 5, if it's a negative, then we add it to it. So we add it to it, so now it becomes 5 becomes negative 3, and 10 is a positive, so it's going to be positive 4. Now we come to 13, right? Come to 13. So at 13, previous is a positive, and I am positive as well. So 13, we need to make a choice, right? Whether we are going to so for a value that does not fit in the previous max, right? So everyone has a previous max in this value. So if it does not fit, so it's going to, so it has to start by itself, or we can actually look previously for, but isn't that O(n) squared? It looks, how do you do the cadence algorithm? So we either choose to follow the previous or we start afresh. Yeah, this is the same. This is the same as the cadence algorithm, but I forgot how that one does. Man, just you learn all those algorithms right afterwards. You're like, oh, I understand it, but then what? Like a week after, you forgot. Oh man, it's dynamic programming, right? There's no question about it. So when we have 13, what is our strategy? And our strategy is the maximum. Well, it has to be the one before it, right? Because the one, so like at 13, we know 10 has a positive difference, and 13 has a positive difference, and that's definitely not good. So for 13, the best choice is the one that's connected to 10, which currently is 5, which we realize that we probably should also include the previous value as well. So the index of the previous value. So 13 will be attached to the previous value. Or it starts by itself. But we know it starts by itself, where we can start by itself. So we pick the bigger one. Starts by itself will be 1. And we follow the previous one will always be larger than 1. So we always follow the previous one. Okay, so we follow the previous one. So instead of having, do we want to record 3 values? Not really. Not really. We can just do, so 13, 2, 3, 4, 5, 6, 7, 8, 9. So for 17, we're going to record 0, 2. 2 is the length. 1 is going to be nothing. So 5 is going to be 1, 3. 10 is going to be 2, 4. And 13, we look to 10, look to the one before it. And then the one before it, we can compute its difference. So its difference is a positive. And then the current difference is also a positive. So we cannot use it. So from 10, we look to 2. So we're to 5. Right? So because 5 must be a negative. So we do 5. So 13, the choice is the previous one. So 13 is going to connect to 2 as well, which is 4. Now 15 is also an increase. So we cannot do 13. We have to do 5 as well, because 5 is a negative. All right, 5 is a negative. So 15 has to do 5 as well. So 15 is also 2, 4. And now we go to, let me just get it. Now we go to 15. Next one, what? Next one is 10. 10 and 15 is good. And then that doesn't matter which one I pick. right? Doesn't matter which one I pick. I just pick 15 because it's right in front of me. So for 10, it's going to be equal to 5 and 5. And for 7, now we're negative again. So we have to go to the one that goes to 10, which is 5. So we go to 5. So 5 will be 5, 5 as well. Now 16 is a positive. So it's going to be 7, 6, and 8 is a negative. So it's going to connect to 8, 7. There we go. We have 7. I think we solved it. Dynamic programming. I mean, it's obvious it's dynamic programming because they ask you if you can do it at ON. Most likely, problem like this is ON. Otherwise, it won't even mention it. Like a problem, usually they solve in ON squared, and then they ask you, oh, could you solve it in ON? 9 out of 10, it's a dynamic programming. Pretty confident about it. All right, let's take a look. We are going to, of course, change everything as usual and put this wiggle in. All right, so what we're gonna do is we're gonna put a DP. DP is going to be you can put as a 2D array. But for me, I don't think it's really necessary. So we're just going to do none times len nums, right? Totally fine. And then we're going to say dp0 is equal to, well, dp0 is going to be 0, 1. Right? We connect to itself. Actually, it's negative. Yeah, let's do negative 1. So because it's a special case, right? Then what we're gonna do is for I n in enumerate nums. Actually no. For I in range 1 to len nums. There we go. That's how it's done, right? And then we're gonna see. You know what? It's actually not right. dp1 is equal to, oh, it depends if there is a dp1. Oh, we can actually do dp1. Can we do it? We just say dpi. Because this one's like definitely works. Yeah, I'm gonna say if I equals 1, which means the second one, right? So we just directly say dpi equals, will always connect it to 0, and this will always be 2, right? And else, this is when we do it. How do we do it? And we say if dpi minus dpi minus 1, right before it is oh, how do we do this? If this is, how do we determine if it's a positive or negative? Is there like a better way of doing this? Sign. Is that a better way to find a sign? Python find sign of a number. Is there numpy.sign? How to get a sign of integer? Yeah, how do you get sign of an integer? Like a quick way. No, I don't like that. Ooh, this is okay. This seems good. Okay, so what we're gonna do is sign current equals this one, right? sign current is this one. Larger than 0. Yes, larger than 0. And the sign previous one is equal to dp as I minus 1, right? Minus, what are you doing? It's not dp. Jeez, man, it's num. Num, this is num. The previous one will be nums, this, minus what? Minus nums, dp, I minus 1, right? dpi minus 1, and we're going to go to 0. So that larger. What if it equals 0? Then it always will be wrong. Yeah, if it's equal to 0, then the signage will be, oof, we have to have a special case. Because if it's equal to 0, it will be false, right? Let me think. If it's equal to, what do we do if it's equal? Well, if it's equal, we are going to, it's just going to be by itself. What if we have equal? If we have equal, we shall just remove it, right? So like for this case, right, this good, this good, this good, and for here, and then these two is equal. So if it's equal, do I skip it? No, if it's equal, I will copy the one previous. Yes, I think that's, I'm going to say if nums I is equal to nums I minus 1, then dp I equals dp I minus 1. I'm going to copy it. Right, so yeah, if it's equal, then actually I don't even have to copy it. I can just do the reference because it's fine. I'm not changing it. Yeah, so now if it's not equal, then we have the current sign is this, previous sign is this, right? The previous sign is this. Because if it's equal, I just use the actual one. Yeah, that should be fine. So this is a current sign, previous sign, right? If the sign is same, if sign current, I think true can be equal to true, right? True equals true is true. All true is true. Is true. True is false. Yeah, let's use is. If this is sign pre, if they're the same, let's do, yeah, if they're the same, right? If they are the same, that means we have to find the previous. So dpi has to equal to dp I minus 1, 0, we have to go that one, and dp I minus 1, yeah, that means it's just a copy of the previous one. If it's, yeah, that means it's just a copy of the previous one. Yeah, which means it's the same as this one. If this one is equal to here, then it's this. If it's this, then it's a copy. It's a copy of the previous one, right? Else, dpi equals, we're gonna do I minus 1, right? I minus 1 and I minus 1 and what? dp I minus 1, 1 plus 1. Yep, I think that is it. So we have a separate situation here. Because we don't want to, you know what, I actually think it'll be easier just to do here. So we can say if n equals len nums, right? If n is smaller or equal to 2, and then return n. Now it's this, and we can put this one here, dp0, dp1, and then I can start from 2. Then I don't need this, I don't need this, so we only have like 2 levels on here. All right, so it's equal, we copy it. Now if the parentheses is this, which means the 2 signage is the same, right? So we say if the 2 signage is the same, then we do, and then we can actually do elif, right? Elif, the signage is the same, then we do this. It's actually, we can do an or because these two are the same. Which means if the signage is not the same, right? That is the case. Wouldn't you just say if the signage is not? What can we do is not? True is false. True is not false. Yeah, we can do is not. So if the signage is not the same, then we do this. Is not the same, right? But if it's equal to 0, then what do we do? If it's equal to 0, then this one will be false. Then the signage will be. Now we still need to handle this situation. Ah, man, this is not fun. All right, no, we don't do that. We still have to handle this, either this or, and what did you do? Or the signage is the same, right? So we have to do either it's this or the signage is the same. Either this or the signage is the same, then we do this. Else, if the signage is not the same, we update. And let's do a little bit cheeky here. Just use one line to represent these two. All right. And then after we're done, we're gonna return dp n minus 1, right? N minus 1, 1. I think that's it. Let's run the test case and see how many we can pass. So the first test case is this. Oh man, I have to handle all the parentheses. Hate it.
I think this works.
Okay, second test case is going to be 7. Oh, I should have a little bit more test cases. Yeah, we have more test cases. That's actually good. Which is 7. Do this one as well. Third one is 1, 2, 3, 4, 5, 6. Actually, just 1, 2, 3, 4, 5, 6. We know what you're trying to test. Alright, and then we're also going to do 1, 4, 7, 2, 5. And that one is going to be how many is that one? The first two differences are positive, so we can do this, this, but not this. Down. So 1, 2, 3, 4. This one is actually 4. Right? Right? This one's 4. And this one shall be 1, 2, 3. 4 is also 4. And this one is also 4. This one's 4. This one shall also be 4. Yep. Alright, let's take a look. Oh, haven't done this yet. Man. Nums answer when I change to wiggle. Nums. Boom. All pass. Let's do this. Copy and paste. Submit. Pending. Judging. Wrong answer. We have a wrong answer. Alright. Do we want to take a look? Let's play around. We know these all pass. Let's play around some. Let's say like we have this, right? A typical case. So this one shall be 1. Oh, this one is 1. Oh, that's correct. We are not right. This is 1. Okay. Where did we go wrong? We go wrong in here. What you're saying is, okay, so we don't do it here then. We just do dp0, right? We do dp0 and dp1. We handle it here. But it's not going to be anything ahead. It's not going to be anything ahead. How should I, like if they're not the same, let me see. So if they're the same, then we're going to copy it. That's good. But if they're not the same, then I'm trying to do is do this and the one ahead of it. So what I can do is to make this a little bit bigger. So instead of this, we can do n. 0 will be so this one will be, the first one will be, oh man, let me think. First one will be, it doesn't really matter, right? What it matters is dp0 and dp1. I mean, we're gonna start from 1. Right, we're gonna start from 1, but we actually, the index is 2. So it's actually dp1 who it connects to. Now it should connect to, so dp0 is, we don't even have to handle dp0. It doesn't really matter dp0. dp1, the first element, is going to be 1, and I'm going to connect it to 1. Oh man, now we have, so the dp is going to be 1 based, but this is going to be 0 based. Okay, that's fine. So nums equals nums, or nums minus nums is larger than this minus nums dp I minus 1. Okay, dpi, so because it's plus 1. So all the nums using 0 based. So currently our index is 1. So we're doing dp 0, and this has to return to dp 1. Yes, yes, that's cool. And then here has to be dp I. Oh man, I don't like this. It just makes things a lot more complicated, but it's fine. So dp I plus 1, because dp is dp's index is 1 based. Num's index. Num's index is 0 based. So this has to be like this, and then otherwise dpi plus 1 equals, this is 0 based and this is 1 based, and we're gonna turn this. Try it. Now we pass. In fact, I'm even sure. Let's also put this, and 1 2 gonna be 2 2 1 gonna be 2. And what if I even do not even do this, right? Even if I don't do this, and this we can replace with n, I think we shall pass as well. Yes, I don't even need this. Now we have the generic case. All right, we're gonna try this solution again. Let's just give it like a good taste. All right, we'll do this one shall be 2. Yep. All right. Oh, what are you doing, man? What are you doing? You copy and paste the wrong thing. All right, let's try this. Pending. Wrong answer. Oh, we still haven't considered some situation. That is very interesting, to say the least. What other condition that we cannot? Okay, let's try 2 2 1 1 3 3. This one shall give us 3, right? Because 2 1 3. Ooh, we find this is not correct. All right, let's make sure that this is 3. All right, I'm gonna try not to. I think I can just refresh it, and then I won't be able to see the. Yep, exactly. So we're gonna do this. This should be 3, but mine gives 2. Yep. All right, this is the next wrong case. Let's see. So 2, and then these 2 will be the same, right? Let's just print out dp. Let's see how the dp look like. Print dp. And we're not gonna do all these. So dp is the dp1. We set 1 1. Yeah, and this one will also be 1 1, which means this we're looking at 1. Ooh. We're actually not looking at a 1. So looking at 1 will be here. So 1, we shall be looking at, because for 1, all right, equals I minus 1. So 0 1 2, yeah. And yeah, this is wrong. This should be 2. Now the reason is dpi, nice, dpi, so I is what? I currently is 0 1 2, I is 2, so dpi 0 1 2 is this one, 1 plus 1. Huh. No, that's not the reason. But why is this still 1 1? Alright, let's take a look. So we are at 2. I is 2. Okay, I is equal to 2. So num's 2. equals nums1. That's false. Nums2 minus nums1 larger than 0. That's true. Is nums1. Okay, nums1 is this. Minus nums dp2. 0, 1, 2. Okay, itself 0. Minus self. This one is minus itself. This becomes 0. So this becomes false. And this will be false. And this is also false. So both, wait, how is this also false? I minus this is false. Oh, false is false. Ah, I see. It is connecting to somebody. So when we are the same, I say I connect to the same value that the previous one connects to. But what if the previous one connects to, we need to, all right, in order to avoid, we need to avoid the, okay, let's see. All larger than 0, so all the consecutive same values, we just turn them into negative. So we don't worry about that at all. I think this is just introducing complexity to our solutions. Yeah, we just have the two loops. Is there a better way to handle the equal? It's the equal. We cannot skip. For this value, I say I connect it to this value, which is not true because these two values are the same, right? So you cannot connect it to this. Does it only happen would it happen like here? No, it will not happen because it will always go front. So okay. What we do is we're gonna just look through. So the only trouble we have is at the beginning. If we have repeats at the beginning, right? That's where we struggle, because if you go later on, even if it's the same, it's fine. So we just need to loop a little bit until we find the first one that is not the same, right? So what we're gonna do, these are all fine, but here we're gonna have a j. We're gonna say j is equal to 0, while what? While nums j is equal to nums j plus 1, right? And actually, and has to be in front. While j plus 1, while j is smaller than n minus 1. And so when we do this, then we do j plus equal to 1, right? So after we finish this, so it's equal, we plus j, and now not equal. Now j is the first number that is not in a consecutive stretch. So the dp is going to be, okay, dp is going to be j plus 1, right? J plus 1 is going to be 1, and it's going to pointing to j plus 2. It's going to point to j plus 2. And then we're going to start from, where are we going to start? We're going to start from j plus 1. That is the next value. We're going to start from j plus 1. And then I'm sure this one will pass. Okay? So this is called, we're going to skip. Let's just put it in here. So this is to skip consecutive repeats at the beginning. start dp at the first non-repeating number from the beginning. Okay, so not at, from the beginning. All right, when you check the rest, ooh, we got a issue. 0, 1, 2, 3, 4, 5, 6, 7. We have index out of range. How is that possible? How is that possible, index out of range? Probably here. Wait, which one? We're talking about 7? 0, 1, 2, 3, 4, 5, 6. This one? Huh? How? J is 0. J is this, and this does not equal. So jump out. dp1 equals. Oh, hell no. This is the problem. So when we jump out, J is pointing to. Oh, where is J pointing to when we jump out? So J is 0, right? Because 0 equals this one is not right. So J is 0. So we say dpi. So dpi is pointing to here. No, dp is 1 based. Here is 0 based. So it has to be this, right? Don't forget, dp is 1 based. And the other thing is 0 base. Okay, now next attempt. All right, let's take a look. Submit. Pending. Accepted. Good. This is how we're supposed to do it. Now if you want to make it hard, you should not check the error case. You have to try to figure out the error case by yourself. And this is ON. So we did do it in ON, and that's ON. All right, let's write the conclusion, and also very soon we're gonna get demoralized by seeing some of the smart solutions other people have. But I am quite confident that this is the solution. We hit all the cracks. I mean, the difficult part. The DP part is not the most difficult, I think. The difficult part is the edge cases, right? We have the repeats. This is the difficult part. And we can make it easier, right? Really make it easier by removing just remove all of them, which is possible, but that will increase the runtime for sure. All right, so let's write it. DP solution. The basic idea is that when we are looking at the ith number, we check the sign with the I minus 1. Let's do I minus 1 number. We also check the sign of the I minus 1 number, and how should I explain it? This is not a good explanation. The DP array holds the max length of wiggle sequence ending at the I plus 1. Yeah, I should say make sure that DP is I1 base. The absolute one's value in DP array holds the maximum length of the wiggle sequence ending at the ith value, ith number of nums. Also, the DP array holds holds the maximum and the index of the number that the ith number connects to in order to create the max wiggle sequence. Yes, this makes sense. This makes more sense. So we iterate through nums and update the DP array. When we finish, the solution, the answer is DP n 1. Holds the maximum wiggle value is a tuple. Yeah, we actually do tuple. Why did you do that? It should be tuple. It's will be, yeah, let's do tuple. I like it to be tuple, which means it's immutable. Yeah, it's important for it to be immutable. So this is fine. So this is just going to be a tuple. It's still in pass everything. Yeah, it's in pass. It's going to be a tuple with the first value being the index of the number that the ith number connects to in order to create the max wiggle sequence that ends at the ith number, and the second value being the length of the max wiggle sequence. Right? The length of the max wiggle sequence ending at the ith number. So we iterate through, yep. For each DP action, we check the sign. We check the sign of difference. We check the sign of the ith number and the I minus 1th number. And the sign of the I minus 1th number and the number right before the I minus 1th number in the max wiggle sequence. If the two signs are not the same, we can add the ith number to the current to the end of the wiggle sequence that ends at the I minus 1th number. If the two signs are the same, then we add the ith number to the end of the wiggle sequence that ends at the number right before the I minus 1th number. Right before. And the number right before the I minus 1th number. You write it this way. I think if I read it again, I won't be able to understand. I have to really read this in order to understand. If the two signs are the same, then we add the ith number to the end of the wiggle sequence of the of the max wiggle sequence that ends at the number right before the I minus 1th number. If the ith and I minus 1th numbers are the same, we simply copy the dp value of I minus 1 of I minus 1th number to ith number. The last tricky part is handling consecutive repeats at the beginning of the nums array. We must skip all of them to achieve a uniform solution. We run our on, and we have 36 milliseconds, which gives us 62% ranking. This is a good question, right? It's very good. Let's take, and we might actually have a solution for this one. Yes, we do. Wiggle sequence. Don't tell me I've done it before. Hopefully not. Yeah, do this. Submission. Yep, I did it today. Description. I like it. 376. Good question. It's a good question. LeetCode 376. All right, solution. Brute force. We skip. DP. ON squared. Linear dynamic DP. ON. Space optimized DP. O1. Space is O1. Yeah, that is true. We can, because we only use it once. So indeed, we only need to have O1. Okay. Greedy. Oh, I can do greedy. Oh man, do you want to look into greedy? Alright, let's see what the DP is the same. Any other could correspond to only one of the three possible. Up position, down position, equal position are done as wiggles up. Then before it must be a down position, so up equals down plus 1. Same as down I remains the same as down I minus 1. If nums I smaller, then it wiggles down. Okay, you can see we'll not change anything because so both remain the same, and this, and at the end we can find the larger of the up, and then the longer to find the maximum. Okay, let's take a look. Up, down. Hold on, too fast. Up and down. Okay, yeah, they can count it both. So that's an up. So if it counts an up, down doesn't change. If it counts as another up, up doesn't change. Down also doesn't change. Okay, so here it's an up. Up equals down minus 1. Down equals to previous. So how many downs we have so far? So it's an up again, so it doesn't change. Okay. So if we have a down, then down will equal to up plus 1, and up doesn't change. Yep. Equals just don't move. Okay. So answer is 6. Okay. ON and ON. It's slightly different. slightly different from my solution. I mean, I will use, it's actually this. Yeah, mine is actually very different. This is an up and down, which means if we find an upper trend, right? If we have find an upper trend, then we need to know the length, the maximum length of the most recent downtrend, because we can connect to that. Yes, so that's, if we have upper trend, then upper will be down plus 1. If we have a downtrend, then I'm going to find the most recent upper trend. So it'll be up plus 1, and up doesn't change. And if it's the same, we remain the same, and then we're going all the way to the end, and then we find, okay, yeah, that's a good solution. That's a good solution. Now, with this, we can do space optimized. The same idea, because or these are wasting. You see, these are all wasting space. We only need to know is 2. Right? The current is 2, and that's the only one we want. Which means if we start, and then we have up and down, just only one value. Yeah, we can do only one value. We don't have to record. Only one value shall do. Okay, so let's write this. I like this up and down idea, which is pretty good. I like the up and down. I think it's I won't say it's more intuitive. I think it's about the same. So this is the solution. This is the up-down trend solution offered by the official solution. All right. So let's try it. So with this, actually getting into the nitty-gritty, it might not be easy to write. So you also have to think about, but we don't have to worry about the repeats. The repeats will be the same. So we just have an up, we have a down, right? Both will be equal 1 to begin with. And then we are going to do, what we're going to do is we're going to loop for I in range from, let's say, 1 to len nums, right? And then we're going to say if nums I minus nums I plus 1 is larger than 0, we mean it's upper trend, then we do not change down, up equals down plus 1. And if this one is smaller than this, then we say down equals up plus 1. And then else, we don't change. And then we return max up, down. Okay, let's try it. And we pass all of them. Wow, it's only, that's quite elegant, huh? This is O1 space. Let's see. This. Yep. Wow, we wrote it ourselves, so I'm happy. O1 space. I don't know what I want to write here too. So I'm pretty sure. What are you doing? O1 space and O1 O(n) time. Okay, the idea is simple. Each number is either on an up or down trend. When it is on an upper trend, uptrend, we use up and down to record the max wiggle sequence, the length of the max wiggle sequence that ends in an up or down trend. Thus, when a number is in an uptrend, it can only be added to the most recent downtrend. So we increment. So we increment down. No, so we modify up by doing up equals down plus 1. Similarly, when a number is in a downtrend, it can only be added to the most recent uptrend. So we do down equals up plus 1. If the number, actually it's if the number is the same as the previous, we do not change up or down. And then boom, all one solution. Great. All right, let's see. The greedy. Okay, the problem is equivalent to finding the number of alternating max and min peaks. That is yes. Since if we choose any other intermediate number to be a part of the current wiggle sequence, the max length of the wiggle sequence will always be less than or equal to the one obtained by choosing only the consecutive max and min elements. This can be clarified by looking at this. If we choose any other intermediate number to be part of the... Okay, so what it says is, yes, so a wiggle sequence is we just need to find the peaks and the valley and peaks, what they call it, the max and min peaks, right? The max and the min, because if we choose anything else, it will either be the same or worse. Yeah, it will either be the same or worse. Choose D as the second point, or choose C as the second. Choosing C as the second point. So we choose A, D, E. We choose A, C, and then we have to go HI. Yeah. So it's always better to choose the peaks. So we just maintain a variable prediff. Prediff is used to indicate the current subsequence lies in an increasing or decreasing wiggle. If prediff is larger than 0, it indicates that we found an increasing wiggle and we're looking for a decreasing wiggle now. And thus we update the length when we find a decrease. Okay, so we're now gonna implement this. So just take a look. First diff count. Diff is not equal to 0. If not is 2. Okay, that's true. From the 2 onward, the current diff, if it's larger than 0 and the previous diff is smaller than 0, or if previous is smaller and the current now diff is smaller and the previous diff is larger or equal to 0. It could be 0, larger or equal to 0. Yeah, that's also a peak. Then we increment the count and then we update the diff. It's good. It's good. Understand it. Oh man. All right, let's take a look here. 3 line. No, that's way beyond 5 line. 1, 2, 3, 4, 5. And just do a your cache. This is just DP, not a DP solution. All right, that's it. We did pretty well. We find our own DP solution, which is it. This is why I said I am a mediocre solver for LeetCode problem. This is a mediocre solution. It works. It even works for ON, but compared to the really elegant ones, you can see the difference, right? There's a lot of there's a lot of things going on. I mean, it does work, but it's just if we say that there is, say, 10 levels for LeetCode, right? Like these people are on level 11. I am on I was in level 6, right? Around level 6, maybe close to 7. I would say that's my current level, which means the easy question we can probably solve without too much trouble. The medium question is usually we can solve, but it take a while. And the ones we solve, we're using problems really bad. And the hard question will take a long time. I think that's a 7, between 6 and 7. I hope by doing this long enough, I can just getting closer to say like 8 or even 9. If I can get into there, that means for a medium question, we will be able to find this solution. And for the hard question, we'll probably treat it as a medium right now. But I think I'll just take time and just see where my intelligence, where my IQ ends. Anyway, that will be it for today. We did a good one. We shall be proud of ourselves. All right, that will be it. I will see you guys next time, and adios.